One of the important components of this chapter is power spectral analysis of linear time invariant systems. So this, if we have the input to an LTI system is white sensor stationary, and suppose that it has autocorrelation function of Rxx of 2, and the output can be described using that. Suppose that this integral is converging, so we have an LTI filter, and suppose that this LTI filter is stable. Stable means that integral of h of alpha d alpha from minus infinity to plus infinity is a finite number. Or sometimes they say, oh, smaller than plus infinity. So if this integral is converging, we call it stable. So in that case, we want to see what is the power spectral density of the input and output, how they are related. So we will prove that we have shown previously that the cross correlation of the input and output is expressed by this equation. So obviously from here, if I apply a Fourier transform, I get S cross power spectral density xy of omega will become Sxx of omega times h of omega conjugate, because the convolution becomes product, and Fourier transform of that is obviously equal to Fourier transform of this one. So we get this one very easily. Similarly, we have seen that Rxx, Ryy, or autocorrelation of the output is related to cross correlation of input and output convolved. Again, if you take Fourier transform of that, you get Syy of omega is equal to Sxy of omega, and then this becomes simple product of h of omega. Now, you can use this first equation and then put it in here, and then you get another equation, Syy of omega, which gives you Sxx of omega times h of omega and times h conjugate of omega. Obviously, this guy is h of omega to the power of 2. So this is equal to Sxx of omega times h of omega to the power of 2. That means that the PSD of the output is equal to the PSD of the input times the magnitude spectra of your LTI filter to the power of 2. This is called power gain of your LTI filter. So the PSD of the output is equal to the PSD of the input times the power gain.